Hello, and welcome to the Global Spaceport Alliance webinar series. Today, we have put together a really exciting panel on powering launch, nuclear systems testing, and safe operations. For those of you who don't know me, I'm James Corsi, Executive Director of the Global Spaceport Alliance. Now, before we get started with the panel, I'd like to just say a few updating comments. First of all, I want to thank our sponsors, RS&H as our title sponsor, Merrick and BRPH as our platinum sponsors, and Parsons Michael Baker as gold sponsors, and HDR as our silver sponsor. Since our last webinar, I'm pleased to announce that we have 3 new members: Key Bank, Space Angel, and Interact. Further, during the course of this year, there's a lot of exciting things happening. As I mentioned in the last webinar, we've established a relationship with the International Space University, and we're going to be putting on an online program with them called Foundations of Spaceport Leadership. It'll probably take place later this summer or early fall. In addition, we're continuing our relationship with the Farnborough International Air Show. And in July, at the air show, we will be putting on 2 separate sessions for their attendees. Also, as we go forward, we're going to do our 3rd International Spaceport Forum this year in Turkey, just before the beginning of IAC. So please, if you can, put that in your calendars and make sure you're able to attend. Looking forward to that conference myself. Further, we're just about to begin the planning for our summit, which will take place in January in Orlando. The theme is going to be advancing global space economies. Now, as many of you know, this particular summit is the opening gambit to the whole commercial space week, which also includes space mobility and space comm. So make sure you put that into your calendar. The next webinar is on July 29, 2026. It's going to be Designing for Launch, Building Spaceports for Performance and Growth. And now what I'd like to do is hand it over to Dave Schleeper with RS&H, who's going to act as your moderator, introducing himself and the rest of the panel. David, over to you.
Thank you. So good morning, everyone. Thanks for being here. Like you said, my name's David Schleeper. I'm a project manager at RS&H within the aerospace group, where we focus on designing those things that it takes to make advanced missions real. And we've been given particular attention to nuclear payloads of all types over the last several years, and specifically how those payloads should be handled at spaceports. So let's be honest, nuclear power is no longer a future mission concept. It's a near-term necessity, and the real challenge isn't the technology of the reactor or the radioisotope itself. It's everything around it. It's the infrastructure, the regulatory alignment, and the operational reality on the ground. And my focus sits right at that intersection. I'm hoping to bridge the gap between the DOE, NASA, spaceport frameworks, all the mission providers, launch providers, et cetera. Today's discussion is about how we move from theory into capability and how we make nuclear payloads not just possible, but routine, how we hit that cadence that we need to hit to do what we want to do in space. We've got quite the group of experts here today who are helping to lead that charge, and I'm excited to introduce them. First up is Joe Vehec of BWXT. Joe's a senior leader with over 35 years of extensive experience in the nuclear industry for both commercial and government nuclear facilities. She currently serves as the Safety Analysis Manager and Safety and Mission Assurance Technical Lead for BWXT. Her diverse experience includes an in-depth knowledge of safety analysis for the current fleet of reactors, new advanced reactor designs, light water reactors, and non-light water reactors. Joe's experience is uniquely suited to evaluating the safety of all types of reactor designs, including first of a kind, and the use of reactors in non-typical environments and applications through transportable, terrestrial, maritime, and space environments. Prior to her role now with BWXT, Jo was the PSA manager at Holtec International and began her career as a consultant in the nuclear industry, supporting risk assessments for many of the current fleet of reactors. With a BS in nuclear engineering from Texas A&M, look at that, and a master's of science in environmental engineering from University of Tennessee, Jo has continued to advance her professional qualifications through memberships and certifications, including serving as the vice chair for two ANS or ASME standards committees, and serving as a technical expert on several other ANS and ASME subcommittees. So with that, Jo, sounds like you're fairly new to engineering. Thank you for joining us today. Next up, our next panelist is going to be Gavin Fink of Merrick & Company. Gavin's a senior mechanical engineer with Merrick within the Nuclear Services and Technologies Group, where he supports complex projects at the intersection of nuclear systems and aerospace infrastructure. Merrick's a multidisciplinary engineering firm providing solutions across all sorts of technology markets. Important for today's webinar, Merrick provides engineering design and testing for both nuclear facilities and launch complex ground support systems, supporting clients such as NASA and other launch providers. The firm's work includes nuclear containment and material handling systems, as well as facility modifications and ground support equipment and test infrastructure, bringing a cross-disciplinary perspective to emerging and space nuclear missions. With over 25 years of experience, Gavin specializes in the design, fab, and testing of specialty equipment for nuclear environments and launch systems. His background includes nuclear quality assurance under NQA-1, development of purpose-built containment and processing systems, in support of launch operations under range safety frameworks such as 91710, one of my favorite documents. His experience positions him to provide practical insight into infrastructure safety and operational considerations needed to enable routine nuclear payload integration and launch. So thank you, Gavin. And finally, we have Pete Frye of Westinghouse Government Services. Pete's the chief engineer and manager of the dedicated space nuclear application team at Westinghouse. He's the technical authority for multiple prime programs involving safe and reliable nuclear power in space, including AFRL's Jansen High and NASA's Fission Surface Power Program. Prior to his current role, he previously led efforts on lunar landers, satellites, aircraft, and turbo machinery. Pete is also the subcommittee chair for ASTM's Commercial Spaceflight F-47.02 unoccupied vehicles. Pete holds a bachelor's and master's degree in mechanical engineering from Drexel University and resides in Pittsburgh. So a big thanks to all three of you for joining. Obviously, your expertise is very applicable here. So now we're going to jump into some questions, start a conversation. First question is going to go to Jo. So Jo, this isn't the first time the U.S. has tried putting fission reactors in orbit. We've done this in the past, in 1965, and maybe it only lasted for 43 or so days. But can you give us a brief history of previous fission programs, domestic and non-domestic, and whether they launched or not? And maybe importantly, what valuable lessons were learned from those projects?
Sure. I'll preface this by all of the stuff I'm going to talk to you about is public domain, so nothing ITAR or export control or like that. So I don't know who our audience is, wanted to make sure that that's clear. But the U.S. has been working on space nuclear since mid-50s. I mean, we started out with the SNAP program. It's the only one that actually launched a nuclear reactor, which is the one you were talking about, SNAP 8. It launched back in 1965. Since then, we've done a lot of additional work on reactors and space propulsion and electric propulsion and all of that, but we haven't launched anything. SNAP terminated in 1973, and it was basically because of funding and prioritization changed over to the Apollo mission, so that's where all the focus went. But it wasn't the last time we worked on space nuclear. We had the SP-100 program. Its original mission was to supply orbital power for strategic defense initiatives back in the 80s. We had the SAFE program, which was heat pipe power systems, which was in the late 90s and early 2000s. That program actually got to the point that we were testing prototype systems at Marshall Space Center, but we never actually flew one. We had Project Prometheus, which was joint NASA naval reactor project. We had the affordable fission surface power. We had Krusty, which is what a lot of people know about, which was a joint NASA DOE project where they actually used low power heat pipe reactor coupled to a Stirling engine power conversion system. That one finished first quarter or so of 2018, so it's fairly recent. It actually did demonstrate the feasibility of small fission power systems for science and human exploration. Jansen, which was mentioned by Westinghouse, was a U.S. Air Force research laboratory project that looked at missions for spacecraft using nuclear power and nuclear electric propulsion. But like I said, of all of these, the only one the U.S. flew was SNAP 10A, which was back in 1965. Now contrast that to the former Soviet Union. Between 67 and 88 or so, they flew over 35 reactors under their Rorsat program. Topaz was in the late 80s. They flew another couple reactors under that. And out of all of these, there was one mishap. Cosmos 954 back in 77 had an unplanned re-entry. That was one of the former Soviet Union reactors. It actually landed in Canada, and there was a major effort to recover it. I don't have any of the details on how that recovery went or anything, but big picture, we've been working on space nuclear fission reactors since the mid-50s. We have flown one in the US. Contrast that to the former Soviet Union, and they've flown over 35 between 1965 and 88. We've got a lot of lessons learned. We've proved feasibility. All we have to do is take the next step and get it back up there.
I think you kind of enhanced the point I was trying to make earlier. We're not limited by technology. We're limited by logistics and funding. Would you agree with that?
I would completely agree with that.
Great. Well, thank you for that background. I'd like to know more about what happened in Canada. So I'm guessing you don't have information on health outcomes or anything like that.
I don't have anything that wasn't made public. So
Gotcha.
there may
Fair
be
answer.
information out there, nothing that I can share.
Understood. All right. Well, thanks, Joe. Pete, I got you signed up next. In your opinion, this is just your opinion, what's the single biggest misconception the industry still has about launching nuclear payloads?
Yeah, good morning, everybody, and thanks for having me in the question. Yeah, nuclear obviously has had a stigma, going back a long time. Any type of anomaly, whether it be space or terrestrial, gets elevated to the public sphere, sort of regardless of the outcome. So, it's no secret or anything that that's generally been the case for the past little bit of our time here. And as Joe is nicely mentioning, some of those programs you can also tie to public perception, for how supportive funding was as it relates to some of those timelines too. So realistically, a lot of the events in the nuclear industry that folks will all resonate with the names and locations of. A lot of that has been very, very dated technology. What we're realistically talking about here, and definitely looking forward, is complete multiple generations of development on safety, on reactor design, on integrating these systems, and sort of the regulation that goes along with all of that. So, first and foremost, would want to be clear to, not only the forum, but the public in general that, for this to be a successful, reinvigoration of nuclear technology into space with a bit more of a commercial flavor, we need to do this safely as an industry. Need to specifically ensure that there's nice, review processes across the entire stack here. Everything from transporting to integration at the Cape to launching to disposal of these things. If any of that goes wrong for any particular entity, whether it be government-led, commercial-led, et cetera, that might set back our industry. So I think those that are, myself included, sort of very near to this topic, definitely want to overemphasize sort of that fact. We don't do anything without rigorous safety reviews. And while some of the systems we're talking about today might still be in the development phase, we would fully plan on completing all of that type of thing, prior to assembly, launch, etc. So that's really what I would want to come across first and foremost is, us in the nuclear industry, safety is everything, and that helps protect all of us.
Yeah, I want to get you to expand a bit. You mentioned this at the beginning of your remarks, and I'm putting my own words in it, but I think when you look at our commercial fleet of terrestrial reactors, that's primarily 1960s and 70s technology. And what we're talking about doing in space, I think your words are several iterations of improvement, not just in performance, but in safety. So would you agree that there's likely larger safety margins in modern reactors versus terrestrial, or what the US would be used to?
Yeah, there's a little bit of a semi-formal notation of sort of reactor generation technology. Generally, the ones you were mentioning there with incidents in the past were either like a generation one, encroaching upon a two. Generally in the U.S., at least, the our AP1000 plant is considered a generation three plus, and the reactors that we're talking about here for sort of space would be generation four plus. So, high level, every time we've had the ability to redesign, redeploy, etc., we as an industry have definitely taken advantage of the opportunity to have even more robust safety, endeavors, whether that be on both the terrestrial side as well as our sort of future space endeavors here. But terrestrially, there's been all kind of safety to make sure that in every possible conceivable accident, environmental condition, et cetera, that you can safely shut down the system. And we would expect that to be true for space as well. That while these systems do need some assembly, potentially testing at launch sites. Again, to do that in a robust manner that protects everybody involved, not just the nearby workers, but also the general population, outside of the spaceport, kind of bounds. So yeah, there's if you want to use the belt and suspenders analogy, that's usually not enough for our industry. Sort of run out of analogies there, but imagine multiple redundancy features. In the you mentioned 91.710. If we invoke the language of inhibits, there's many inhibits along this technology stack to make sure that it remains safe, prior to operation. And that's sort of, again, standing on the shoulders of giants of every lesson that's come before us, whether it was terrestrial or even Soviet, in nature, taking those lessons learned and truly trying to adopt them, not only into designs, but to industry consensus standards, into regulatory, affairs, etc.
Understood. Thank you, Pete. And before we move on to Gavin, I forgot to mention that please drop all your questions in the chat. We will get to them. Trevor, I saw yours. I think we have a question coming up for Joe here shortly that would tie in nicely to that. So I've seen it. I will get it asked. I'm going to pause it for just a minute. Next up is Gavin Fink. Gavin, I'd like your take on, are spaceports ready today for nuclear payloads, or are we still in a pilot phase of figuring that out?
Yeah, thanks. Good morning, everybody. And I'd like to say thank you also for including me on this webinar. So I would say, some spaceports currently handle nuclear payloads. We've done a lot of nuclear missions in the form of, RTGs, which are radioisotope thermoelectric generators. But the current discussion is around, flying space reactors. So the upcoming missions like NASA's LR1 and SR1 are in the near future. So, currently, spaceports have some capability. We've certainly done it from, our major spaceports here in the U.S. But I expect more spaceports to add, nuclear payload processing capability in the future.
Do you envision, I'm sorry, go ahead and finish. I'm sorry.
Okay, yeah. So the next missions that launch space reactors will be, somewhat pilot phase. There'll be kind of data gathering missions to, create, new data sets that, we can perfect, these launches, and, going on into the future. So we're not talking about, spaceports having to become like a licensed nuclear reactor facility, because you're not going to be operating the reactor on the ground, right? It's going to be put on the spacecraft. It's going to be launched, and then when it's in space, the reactor will be essentially turned on and producing power. But until then, it's in a pretty stable condition, I would say. And so there's, it's not a reactor facility. Spaceports are they're going to have controls that they're somewhat used to, maintaining the payload and keeping it secure before launch.
On the topic of spaceports, what
Yeah.
are you envisioning here? Are you picturing multiple spaceports trying to launch nuclear payloads, or a few select spaceports increasing their infrastructure to handle more nuclear payloads, or is the answer C, all of the above?
Well, initially, we're talking, Cape Canaveral, East Coast, and then Vandenberg out of the West Coast. I think those would be, probably the first spaceports to do this, and who have done it in the past. But yeah, to bring on new spaceports, there's going to be, the same rigor that the two main spaceports in the U.S. have gone through. The same safety analysis and risk analysis that's been done to ensure safety for the the public and the environment.
Understood. Thank you. So, Joe, we're going to come back to you now, and I'm sure this is on the mind of a lot of the people watching this, especially if they're fairly new to space nuclear. So, could you walk us through, I guess, what an SPM-20 is and the flight approval process for it, and how that incorporates safety into the approval process? We've heard safety and risk analysis several times already, so I want to just really focus in on how all that aligns with NSPM-20.
Sure. Big picture, NSPM-20 is a presidential memorandum that came out that basically says, here's how we are going to do space launches for, nuclear fission space launches. And it sets out the ground rules. It is not the actual regulations. It's the thought process behind it that gives us, here's what we have to do. Here's the different tiers for how we evaluate the safety and stuff. It was signed in August of 19, so it's not that old. Have we done a whole lot with it? No. It's really only applicable to the launch phase, so it does not apply currently to the transportation, integration, anything like that. This is simply for launching. So that's one of the first misconceptions about it that a lot of people have. But big picture, it's a tiered process. It's non-prescriptive. It's probability and consequence based. The higher the consequences, the lower the probability of having a mistake or an accident has to be. So basically, if you have no consequences or very low radiological consequences, I think same type of exposure as you would from an X-ray or a weekend trip to Denver, then there's no real risk threshold that you have to worry about. But if you have a major consequence, think Chernobyl type, then you have to have a probability of less than 1 in a million, so to speak, of that ever having the potential to occur before you can even consider doing this. So it sets out the ground rules for how you look at what the risk is and know where to focus on your design to get rid of the risks. Now, to make sure that this is all evaluated properly, a safety analysis report is developed, and all of the scenarios that are postulated are analyzed, and the worst consequences to the public are evaluated. And this report actually goes to an interagency review board to make sure that nothing was overlooked. I mean, the INSERB is what it's called, has Department of State, Department of War, Department of Energy, Department of Transportation, NRC, EPA, NASA, technical experts from across all of the major departments to look at it to make sure we don't miss something that would impact them. Because we're not only looking at public health and safety, we're also looking at environmental health and safety. So it's a really rigorous safety review that's done to ensure there's no undue risk to the public or to the environment. Now, right now it's focused on launch, so it's focused on Earth type impacts, including reentry. But there is a provision in there for additional guidelines for off-planet and orbital type of operations. Those have not been fully developed, but we're expecting them to come so that we can, make sure that we're not limited to just potential impacts here, but we're looking for the future also. So does that answer your question?
I think so. And I'm going to follow up with a question that Trevor put in the chat. He's referencing some stuff Pete mentioned, but there's also been advances in regulation or the regulatory framework of system design for these things. Do you have any feedback on that or any thoughts?
A lot of the newer designs are passive designs instead of active. The current fleet, as we call it, all of the reactors we're used to having here rely on power, rely on operating systems and stuff to be able to shut them down and put them in what we call a safe, stable configuration. The newer designs are passive, which means they don't rely on power. They rely on passive type of operations. Here on Earth, it's stuff like gravity, natural circulation, that type of stuff. In space, you don't have the gravity, so there's different focuses, but it tries to get rid of the need for outside supports to get you to a safe configuration.
All right. Thank you. Pete, you're next on the docket here. Pete, I really wanted to ask you this question. So you've got that background in getting payloads into space. You know what that process is like at a spaceport. Can you explain to us what's fundamentally different about integrating a nuclear payload into a launch campaign versus a conventional spacecraft?
Yeah, and let's I guess in the spirit of your question, let's talk a little bit about radioisotopes maybe first, and then moving to fission too. As mentioned a little bit earlier, we do fairly regularly compared to fission launch radioisotope based systems. So just for those that maybe aren't fully aware, as an example, NASA's what they call the MMRTG, which is a plutonium-based design. Generally, what happens is you assemble that into a kind of a chassis magically with the nuclear PhDs, and from that point forward, it is now outputting radiation. So anytime you're near that, anytime you're handling it, transporting it, whether it's from that assembly site to the launch pad, on the rocket, on the spacecraft, it's outputting radiation that entire time, as well as heat. So the protections that you need for that from a spaceport perspective, in always sort of in a radioisotope world, keeping that system cool is the name of the game. So, as an example, Gavin mentioned the Florida based launch pads, particularly in the summer there, as folks are aware, pretty hot if you're not careful or if there's a loss of power event at the facility. You would take precautions on when you actually ship that based on weather, based on, as late as you can integrate that into the flow to minimize, dosage and worker protection, kind of events. So there's very specific things you need to do to handle that, generally characterized, but again, semi-novel if you invoke sort of the commercial outlook of these systems, say for lunar night survival, as compared to a NASA-led mission. So jumping to fission quickly, again, from just a design perspective, the interesting part about the reactor is that we have control over it. So we can proactively ensure that we don't start that reaction, that chain reaction that ends up fissioning and then creating the equivalency of heat. We don't start that at the launch site. We do that later in the mission, as Gavin mentioned. A bunch of aspects of that, all involving safety that we can get into more in detail if necessary. But so what that means is the reactor can be there, people can be around it. It does have essentially a bunch of potential energy, if you will. But inherently, if you have enough inhibits and safety protocols, the reactor's not doing anything. It's not on, it's not operational, it can't physically turn on without very specific instructions sent to it. So therefore, the protections you might want from a spaceport perspective maybe look a little different than a radioisotope. It is more around the accident side of things, that if something goes wrong, there is again a good bit of potential energy and kind of stored energy in this type of design. But a similar, but just at elevated levels, similar things exist on spacecraft, right? Hydrogen isn't the safest of chemicals. It requires specific handling. You wouldn't have someone come off the street and start, hooking up the plumbing. So that would be similar for the nuclear-based systems. Anytime you would be near the reactor, touching the reactor, handling stuff on the spacecraft that could, potentially lose and inhibit. Again, training and having the right people in place to do that. But the facilities are less. The consequence could be higher in an accident, but the demands on the facilities are less. So hopefully that was at
Less
least an
on
overview
fission
of the
versus
two paths.
radioisotope.
Right.
Okay, got it. And I'm going to hit you with Samantha's question here. In your opinion, what capability doesn't exist today that must absolutely exist before nuclear missions occur at scale? I guess you go two ways with that. You go on the space side. Is it on the reactor or that platform, or is it on the infrastructure side on the ground? I'll let you answer that however you see fit.
How about I do both slightly, if that's okay?
Let's do it.
From a reactor perspective, the uh, sort of novelness here has different motivations than the terrestrial fleet. The terrestrial fleet of reactors is very, very dominated by the cost of energy production. So, saving money, keeping everybody's electrical bill sort of low is the name of the game. What that results in is low enrichment uranium. It involves fairly large, compared to space flight hardware, fairly large reactors. And again, there's nothing wrong with that. We've been operating these since the 50s. But when you go to space, it's a much more impactful mass target. Therefore, most of these conceptual systems have used a higher enrichment level of uranium. We Typically the notation is sort of low enriched uranium or high assay low enriched uranium or highly enriched uranium. You typically fall in one of those three buckets. So a lot of these early concepts, and at least in the past maybe decade or so, a lot of attention on HALEU production, which is the fuel that would go into this. So on the back end, just the in the world in general, there definitely are some supply chain challenges around getting these reactors, designed, built, etc. But as I'm sure this forum is aware of, the amount of payloads going through launch sites these days is only increasing, and that's a little bit different than the nuclear safety culture of, hey, the first couple of these we might want some extra time at the facility. Maybe instead of your 15 or 30 days flow, maybe we want a little extra time just to slow down and do this cautiously. So as an example, asking for additional time at the launch site is more of a challenge these days than ever. Having enough capacity is one thing. And then just to maybe end the thought, the while we're here on Earth, Joe did a lovely description there of kind of the launch approval process. Prior to launch, the Department of Energy and/or the NRC have pretty clear jurisdiction on what you can and can't do, at least in the United States, with fissile material. So, as an example, you can't just put the uranium fuel in a reactor wherever you want. You need specific licenses. You need specific facilities that have gone through the review process to be able to do that. So as an example, as we scale this system at spaceports, that's a very coveted license that the nuclear folks would like to take advantage of. Currently, without maybe disclosing too much information, we do a lot of the assembly offsite prior to arrival, which means we invoke additional penalties and pain both on the design and transportation side due to the launch site limitations. And that would be a great restriction to sort of remove. But to do that, again, at least in the US, we need to do that under the NRC jurisdiction.
Great. Good response. Thank you. Gavin, you're up next. I also have a good chat question for you that we're going to hit you with after this first one, but I think Pete touched on this a bit. What new infrastructure is non-negotiable for spaceports that want to support nuclear missions?
Yeah, thanks. I'd probably, reiterate some of the things we have said before, but non-negotiables, your facilities are going to have to be nuclear capable payload facilities, just to be kind of basic. But you think about the storage and security of, and custody of the material. I think spaceports have access control and things like that already, where security is already highly important. But some other things like radiological monitoring is probably going to be a necessity. These fuel forms we talked about with fission reactors, some of them are, just inherently safe before launch. But like, how do you prove that, right? You monitor to make sure that the configuration of the reactor is as expected. Other infrastructure, you have to prepare for launch accident and maybe dispersal mitigation capabilities. So facilities and infrastructure will have to be in place to, plan for those type of events. And then security and emergency response systems. How do we, in the case of an emergency, how do we get the things under control, I guess, and mitigate, harm to people and the environment.
All right.
So I already said, some fuel forms, we've talked about them. They like the triso fuel and things like that are new fuels being developed and tested currently. Those have inherent containment built into them. Other fuels that may be used on upcoming missions are going to be different than that. So there'll be a separate containment, and there's going to be different safety functions that we have to develop for those.
All right. Again, just asking for your opinion here. Not going to hold you to it, but who pays for this type of infrastructure and personnel support? Do you think that comes from? Is there going to be ROI for a commercial investor, or does this need to be largely government supported?
That's a good question. I don't know if I have the answer, but I know it's been, I've watched some other webinars and stuff, and the big, launch providers have asked for the government to pay for some of it. They're currently operating at, Cape, leased facilities and things like that. And they're building them out and adding value to these spaceports. But oftentimes, these launch providers are paying for it. But they would love to have, government fund some of it.
Gotcha. All right. Well, thanks. Joe, we're going to boomerang back around to you. You're very familiar with the regulatory requirements in this field. So the regulations that are in place today, are they more conservative than they need to be, the right amount, or not conservative enough?
Okay, this is my own personal opinion, so BWXT can't get mad at me or nobody else. But having worked on Draco and trying to get through the regulations to figure out how we're going to get the reactor to the processing facility, get it integrated, then get it launched. The only piece of it that really had any really firm applicable regulations was the launch side of it. The rest of it was trying to fit a square peg in a round hole. There are regulations, but they were designed for other applications, and they don't really work directly for a space nuclear propulsion or space nuclear electric system or anything like that, simply because if you look at like the transportation related requirements, you have to have a type A or type B package depending upon your fuel enrichment. But these packages were designed for spent fuel or for irradiated materials, not for a new unirradiated, non-operated complete reactor core. So your accidents of concern are different, and they weren't developed for the accidents that we are concerned with. Like was mentioned by one of the other panelists, this is a new core. It's never been operated. We don't plan on operating it while it's on Earth. So our biggest consideration or concern is having it go critical when we don't want it to. So an inadvertent criticality, not a release of radiation. The transportation requirements are focused on a release of radiation, but we don't even have that as a real concern at this point. So it doesn't work really well. The other thing is a lot of these reactors, if we're doing fission type reactors, are going to be fully assembled at the manufacturing facility because that's where the license is for creating the fuel and putting it in the reactor. And then it will be transported or need to be transported to the processing facility. Once it gets to the processing facility, though, we don't know what type of license it's going to require because it will be different depending upon if it's a government facility, which can have nuclear indemnification, or if it's a new commercial facility, which may need an NRC license. We're not sure. And then what will that license allow you to do? Can you do testing on it to make sure that your control elements, for example, are connected properly and working? That your assumptions with respect to how much radioactivity you get when you turn a control drum or pull a control rod or like that are actually what you see when you start to, look at your core that was designed and fabricated and built and shipped out. How do you get it from a processing facility that's not on government property over to a launch facility that is, when you have to go across non-government roads that are applicable to DOT and NRC regulations that require a type A or B transport cask, but you're integrated into a fairing that does not meet those requirements. So there's different considerations like that where I don't think the current regulations fully work. I think we could take NSPM 20, expand the basic rules and thoughts under it, and get the right regulations in place. But right now, in my opinion, the regulations are overly constrictive. They're resulting in us doing over-design, which results in overweight and overcost for the reactors, and we need to streamline that in order to make this feasible for the cadence that we want to get to.
So if I'm summarizing this correctly, your opinion, not BWXT, is that the current regulations are meant for commercial reactors, not so much space reactors, and we're trying to shoehorn space reactors into commercial regulation.
Their current regulations are designed around the commercial fleet and spent fuel, not new fuel that's fully integrated into reactors that have never been operated. So there's a difference in what your transportation requirements should be, where you can do your testing and what level of testing should be done, that type of stuff. And none of that is really fleshed out yet.
Okay. All right. Well, thank you. All right, Pete. So we're going to come back to you now. What has to happen for nuclear payloads to become routine in the commercial launch sector? So to hit the cadence that whatever the demand is.
Yeah, I think we're trying to take the lessons learned from the past programs that maybe didn't get to the launch pad, to heart. The sort of revitalization of this in the past maybe five years, and most recently within the past maybe 6 months with some of the NASA announcements. There's a lot of revitalized interest and whatnot here. Piggyback on what Joe said, there's a lot of unanswered things to sort out here to truly hit these at some type of cadence. I think for these first, even one would be a success. For the first one, let's say, really probably need a whole bunch of people coming together, both on the government side, the industry side, to sort out, what the right process, design, safety classifications of these are. Because it's as Joe mentioned, there is some uncertainty on how you would do that, and I don't think that the demand is necessarily the problem. If we translate this to low power for a second on some of the radioisotope things, if you take a look at what NASA has done under the Commercial Lunar Payload Services or CLPS model of sending lunar landers, in general, it's nearly impossible to survive the lunar night without a radioisotope or some type of fission reactor, on board or nearby. So the folks doing those types of missions are typically planning for, no more than a 14-day period of time on the lunar surface. And you can imagine, missions that cost 100, $200 million for, I don't know, 10, 14 Earth days of time doesn't really hit that much on some of the scientific and exploration goals that we have for that. So if we're able to show that this is able to be done safely and commercially, that would help a whole bunch of folks, outside of this call. But again, piggybacking on what Joe said, no one's ever tried to do that commercially. So indemnification, again, for those that aren't aware, is essentially a necessity for any of us in the nuclear industry. That these types of accidents and whatnot, if they occur, are substantially more than any commercial entity could ever handle or insurance market could ever handle. So that's been the name of the game for for a long time now on the commercial fleet is sort of that government assistance. So I think that's what we're also hoping for here on sort of the space nuclear side is, we're very excited, maybe speaking in general for the space nuclear industry, we're very excited for NASA's endeavor here under the first nuclear electric propulsion demo, SR1, that hopefully pathfinds a bunch of these questions, infrastructure, regulatory questions, so that when the next kind of iterations of these come, i.e. LR1, at least in NASA speak, the commercial industry is right there and willing and able to support it.
Great. Thank you. All right, Gavin, got a question for you here. Pete talked about this a little bit a few questions ago about how the reactor is going to arrive, probably already assembled with fuel, and that drives the con ops downstream, and they'd like maybe some more flexibility on that. And some of that is driven by not just the capabilities at the spaceport, but what testing can be done before it even gets to the spaceport. So I want to talk about testing a bit. What type of testing can the industry expect that would be beyond conventional for nuclear payloads? So not for terrestrial reactors, but what would be specific for these space applications, and what types of facilities and facility capabilities do you envision, and are they available?
Yeah, great question. And I, kind of as this webinar has developed, kind of my thoughts on this have maybe changed a little bit. So what I was thinking of was, nuclear payload integration is less about assembly and checkout at the pad and more about testing or certifying everything offsite, and only perform controlled low risk operations at the spaceport. That's kind of what, we've been talking about, but is there maybe a chance that we do some testing at these spaceports and things like that? I won't answer that here, but I'll talk a little bit more about what testing might be needed offsite. And, the philosophy, in aerospace is test like you fly. And now that means, incorporating the nuclear environment into tests. So we talked about the nuclear fuel forms and the containment around those fuels. And this has somewhat been pioneered by, RTG missions. So for testing that they did for that, they did impact testing, impact survivability, where you think of a high velocity impact, making sure that fuel form or what happens to it and study it and make sure in an accident scenario, it can be safe. There's also fire or thermal excursion testing to simulate, what happens if, the vehicle catches fire or explodes. So you want to see that the fuel form can handle the temperatures, or, you test for that. Fragmentation resistance, some of these fuel forms are encapsulated and somewhat strong, I would say. But you got to test it to see what it can go through, put it through its, credible explosion tests. And then there's, dispersal behavior. If there's an accident, you'd want to do in a controlled way modeling of that or testing of it. So I said, this is kind of what was done for RTGs. Talk about what facilities exist today and maybe what they might need. There's current facilities that, already test, the vacuum of space and, thermal vacuum chambers, where, the coldness of space and the vacuum of space. But now think about doing that combined with, a nuclear, a radiological field, a source term that's going to be, hitting everything on that spacecraft as it's flying and the reactor has gone critical in space. You want to be able to test and make sure your hardware, think sensors and everything else that you need to survive in a radiation environment, so that you get that data. And so I think some sort of combined testing, maybe separate testing, but the best type of testing is, testing like you fly. So combined testing, I think would be ideal.
All right. Yeah, I understand that. I'm going to hit you with a question from the chat real quick. I'm trying to condense it a bit, but are there additional considerations for payload processing, let's say at a spaceport? So I think Joe alluded to the fact that we'll probably need some sort of criticality detection, but are there other considerations if we're going to be lifting let's call it a field reactor with a crane, non-operational reactor, but operations of that nature?
There's certainly codes and things that, handling nuclear items on a crane that you'll have to meet. So I'm not saying that those facilities don't have that capability, but you're going to want to certify your facility cranes to those nuclear standards.
Okay, it's probably some training involved and some background work there. Okay.
Yep.
Well, with that, I want to open this up to the Q&A within the chat process here. Don't have much else to ask these guys, not queued up anyway. Let's see what else I have. Yeah, nothing's coming in on the chat. I think there's one more question here. Based on your experience, how are the evolving and ongoing infrastructure requirements of a spaceport managed? Additionally, what criteria or threshold are used to determine that these requirements are sufficient, at least for a period of time? Gavin, you're kind of the spaceport guy here. Do you have any insight on that?
Reading the question again, based on your
based on your experience. I'll let you read it. You can read it.
Well, I think we talked about the safety and risk analysis. Those are going to determine what the acceptance criteria are. So how safe is safe enough type of thing. I don't think they're developed today. I think that's, future work that has to be tackled. But yeah.
And Joe, if I heard you correctly earlier, it sounded like you were suggesting the possibility of maybe expanding the mindset behind NSPM 20 to ground equipment, ground operations as well.
Yeah, there are some new companies or some companies that are building spaceports right now that are going to have multi-bays in them. And one of the considerations that we have to look at is if I have nuclear in one bay, I'm not necessarily discussing that with the people who are 2 bays down from me, but we have to make sure that the infrastructure keeps everybody safe. So that's some of the stuff that I think the common sense language out of NSPM 20 can factor into to help make sure that it's safe for everybody, not just the people working in that one bay, and make sure that, we handle it properly, but we don't expose potential, non-needed information to people who are there working on a different payload for a different launch. So stuff like that,
Gotcha.
to me, I think the NSPM 20 framework could be used to help set up.
That makes a lot of sense. Pete, you get the last shot here. Any reflections on the insert process?
Yeah, I was hoping to address that one. Thanks for the question there. The for folks that aren't aware, prior to that formation, there was I don't know if officially the right term is ad hoc, but I'll call it that, an ad hoc panel that did a similar function. And what NSPM 20 did was sort of convert that panel into a standing board, with official seats and whatnot. So I have been I have had the pleasure of presenting to that board a few different times, and in general, I think the process the process has not been fully exercised to date from start to finish. Draco, Joe mentioned earlier, was sort of leading the charge for a little while. Seems like the NASA SR1 mission will now maybe take that torch. But for a couple of us that have been in the sort of early phase or phase one of the INSRB process, in general, I think that board is a welcoming community. They're every individual on that, as well as sort of the folks behind the scenes, very knowledgeable on what we're talking about and bring very interesting perspectives, across their different agencies that bring the board there. As far as what might that entail, and maybe some rhetorical questions that I'm not going to know the answer to myself, but things we've asked in the past are how might information be shared across that when you're dealing with maybe individual, proprietary, maybe even classified designs for the Department of War side. How will maybe lessons learned or other types of helpful information be shared across other members? It's not exactly a public thing, i.e., all of those meetings are held privately. Some of the process that comes out of that, i.e., like the environmental NEPA process, obviously there's a bunch of public things that come out of that, which would be work products from this board. But again, without having folks exercise the full end-to-end in the past, it's a little uncertain how that will go. And I think, I'll just put my 2 cents in personally. The fear is that maybe someone has some type of requirement that's not maybe well written down, and you don't learn about it until late in the flow. As you can appreciate as a nuclear designer or spacecraft designer, or even spaceport designer, late requirements, usually result in something bad, i.e., more money or time or delays or whatnot. So I think that's sort of the rhetorical question of how will that be operated sort of long term? How will we as an industry be able to benefit from that as compared to just sort of private little pockets of folks that maybe know something that can't be shared?
Thanks, Pete.
Hey, David, I can give you a little bit of insights on working with the insert board. They are meeting on a regular basis. It is now a stood up board, and they are very open to having questions and discussions before any formal presentations, which makes it a lot easier to make sure there are no jump up surprises at the end. Having presented a preliminary SAR type analysis to them, all of the comments and questions we got were very technically sound. They were not design or, specific to that. They were big picture type questions. Did you consider this? How did you do this type of evaluation? They did not look at the design specifics, so we didn't have to worry about a lot of IP getting into the wrong hands, which was very nice.
Good to hear. Good to hear. All right. Well, so before I hand it back over to Mr. Causey, Joe, Gavin, Pete, thank you guys so much for the time, not just today, but all the prep work for this. I very much appreciate it. Thanks for going out of your way for us. And James, I'll hand it over to you.
Okay. Let me just echo what David said. Peter, Gavin, Joe, David, too. Thank you so much for your participation in this panel. I sat riveted, learning an awful lot as a result of doing it. We did record this session, and as soon as Izzy gets it done, it will be posted on our website. So if you wanted to see it again or you wanted to share it with others, it'll be up certainly within the next week to 10 days. With that, this terminates the webinar. We look forward to seeing you again in July. Okay, take care. Thank you very much, everybody.